Good morning, afternoon, evening. Welcome. Thanks for joining. I've got a little bit of presentation here on EIS for difficult samples and a little bit of quick information from the outset. So we have several webinars up now on EIS, so I'm not going to be explaining what EIS is or how to run it in general. This is more to focus on improving the actual measurements that you get with samples that are fairly challenging. If you want to go back and take a look at those afterwards to actually get a better idea about EIS, that's a good idea. And with that, here we go. So this is what we're going to cover today. So the overview, we're looking at just how to get the best answer from the EIS sample, from your EIS system. We're going to go through what difficult samples are, the limits of the measurements, in refresher on instrumentation, what the EIS performance limits are, ways to make bad measurements, and then how to improve those. So what are difficult samples? For EIS, there are a few general categories of difficult samples. The big ones are high impedance and low impedance. So high impedance, where these terms really, what they mean will differ from instrument to instrument and from system to system. For our potentiostats, high impedance generally means giga-ohms plus. Depending on exactly where you are, what system you're using, you might start to have issues when you get up into the high mega-ohms region, but giga-ohms and higher, you're definitely going to need some special considerations. Samples that have this level high impedance are things like coatings, very small microelectrodes. On the other end is low impedance. When the impedance gets low enough, again, there are issues. And for our systems, we tend to mean less than 1 milliohm. You have to have special considerations when you get below an ohm in terms of whether you're just running potentiostatic or galvanostatic EIS. But in terms of actual difficulty in making the measurement, it's when you get down into single-digit milliohms and microohms that things really get challenging. Systems that are in the low end of the impedance range are batteries, double layer capacitors, fuel cells, and very large or porous electrodes. There are other types of difficult samples to manage. Unstable samples are actually very, very common. You get them in batteries, you get them in corrosion, you get them in biological systems. Anytime where the sample changes versus time, you have a potential issue where you've got instability, and instability leads to invalid EIS. So this is a fairly common sample problem. And then there are plenty of other difficult samples to measure. If you've got high temperature pressure considerations, you're in an autoclave, that brings up grounding issues, whether that's in the autoclave or there's also grounded electrodes. Some samples are themselves more difficult to manage, things like curved surfaces. And you can have reference path impedance issues. So the sources of these limitations are kind of shown here, broken down. The cell cable. This is listed first because it hits a lot of limitation issues. So you can use the configuration to improve the limits for your cell cable. For low current measurement capability, you want to use a Faraday cage, which blocks external noise sources. Additionally, the low current range of a potentiostat puts a hard limit on the current measurement capabilities. High impedance means low current. So low current measurement capabilities are what end up being limiting for, especially on the DC side or as you approach DC for impedance. For low impedance systems, low voltage measurement or controllability. Usually it's on the measurement side, you're doing galvanostatic test. Low noise systems are going to have better measurement of low, small voltages, microvolt changes. Also, going into specifications, CMRR, which is the common mode rejection ratio, having that value be very large means that you're going to be able to better measure very small voltage signals even in the presence of a large current signal. There are also the reference electrode and path issues showing up down here. Reference electrodes on the cell side are the single biggest source of limitations and issues. There are additional setup challenges, and then you've got the actual sample. And if we take a look at these, we can break them down into limitations that are put on by the potentiostat itself and limitations that we actually are dealing with that are on the cell side of things. So because the potentiostat itself was, it was a bigger box, but it's not necessarily more limiting in most cases, but that's the one that we're going to spend the most time with here today. So electrochemical instrumentation, brief overview here. A potentiostat is an instrument that measures and controls voltage and between a working and a reference electrode, and generally measures the current flow between a working and counter electrode. Galvanostat is kind of the opposite of that. It's a device that's going to control and measure current flow between the working and counter, and generally measures the potential between the working and reference electrode. Modern systems usually can work as both a potentiostat and a galvanostat. Additionally, they can work as a ZRA and an FRA, and the FRA component is relevant for EIS, but it's the potentiostat galvanostat side of that that we really focus on. Force and sense terminals. High-performance potentiostats are always 4-terminal devices. There are 2 terminals, the reference and work sense leads, that are sense terminals. Those measure cell voltage. The other 2 terminals, the other 2 leads, are the counter and working leads. These are the force terminals, and they carry the cell current. So a lot of time you will not use the force term very often, just call them the current carrying and the sensing leads. When you actually connect all of these up to a cell, in most cases, you've got, or most electrochemical experiments are done using a 3-electrode cell. So your working and your working sense, both the current, green, and the sensing lead, blue, are tied to the working electrode. The white, the additional second sensing lead, goes to a reference electrode, and the additional force lead or current carrying lead, red here, goes to the counter electrode. Because we've divided this into 3, we're only measuring the potential difference across the working electrode surface and up to this point within the solution. But since no current is flowing here, we're not directly measuring any reference electrode impedance, nor are we measuring any impedance or voltage drops associated with the current transition onto the counter electrode. This is just another diagram of the same. You see working electrode and the working sense leads here, counter to the platinum wire, and reference to the pin that goes up to this reference electrode here. That's 3-electrode, 4-terminal, but a lot of devices being measured are 2-electrode. Sometimes it's in a cell, but there's reasons you can't get an actual reference electrode in there. Sometimes they are packaged as 2-electrode, 2-terminal devices like batteries and fuel cells. Potentiostat doesn't have any issues with making measurements on this. Instead of having the reference lead going to an independent reference electrode, it just goes to the same terminal as the counter electrode. So this doesn't change any, it's just moving one lead over. A lot of times in terms of if people are having trouble making measurements, one of the first things that we will ask to do is switch. If you're using a 3-electrode mode, switch to a 2-electrode mode. This is going to come back again to the reference electrode, causing problems for a lot of samples, but you've complicated the system, but you've reduced the impedance loads on the system. So this is 2 electrodes set up, 2 electrode connection. However, the 2 electrode and 4 terminal are kind of different ways of looking and thinking about this, and I'll try and keep my nomenclature the same throughout. 2 electrode means that there's actually 2 distinct electrodes in the system. If you're talking about something like a battery, those 2 electrodes also have single terminal points, and they're sometimes called 2 terminal devices. But we are measuring with a 4 terminal device. So if we connect a 4 terminal device to a 2 electrode or 2 terminal system, we can actually connect that in 2 different ways. One of them would be that 2 terminal setup, where we short our sense and force leads together before connecting them to the terminals or the electrodes themselves. The other one, and the one that's particularly useful for both for 2 terminal devices, but also for very low impedance measurements, is a 4 terminal connection. And what's happening is we make, for 4 terminals, even though there's 2 electrodes, we are making distinct connections for the sense and the force leads. So you can see here a 2 electrode schematic. We've got we're pairing our current and voltage sense leads together and then connecting them. And so in that case, we're going to measure a resistance through this wire, then the cell impedance, and then an additional wire resistance here before we get back. By making a 4 terminal connection and by connecting the voltage leads separately to the wire carrying the currents here, instead of shorting them with the current carrying leads, we actually bypass and we do not measure these resistances. For high impedance systems, this doesn't become terribly critical. These connection resistance, wire resistance, tend to be in the milliohms. So making the difference between 2 terminal, 4 terminal setup is negligible. For low impedance systems, however, that a few milliohms can make a large difference. So Eis System Performance. It is very important. As I've said, a lot of the limitations in difficult samples are difficult because they're pushing up against the limits of the system. So you really want to understand what those are. We can only talk about them in idealized terms because every system and setup environment is going to be slightly different. It's a very good idea if you're up against some of these limits or getting close to them to test things yourself and see what your actual system limit is in practice. That said, we publish accuracy contour plot. You can also get this for a lot of different potentiostats. Manufacturers will have these. They're not all the exact same, so you can't necessarily directly compare them. You really need to pay attention to whether or not the accuracy contour map is done how it's made. For our systems, we use the actual cell cable and we use realistic typical operating parameters for EIS. That is, we're using an RMS AC voltage of 10 millivolts or less. We are using potentiostatic control for the high impedance side. We are looking at galvanostatic control for the low impedance side, and we are using the standard cell cable. When you're looking at this, you can see the impedance range, bandwidth over here, at various frequencies. And what happens when you get down to very low frequencies, you're at hardware limits. So on the high end, this high end limit up here has to do with low current range, the lowest current that the system can accurately measure. It's also coupled with things like system noise. At some point you end up with you can make lower current ranges, but when you get to the point that you're dominated by thermal electron movement, it doesn't really help you to go. So below a certain, and additionally, you've got the printed circuit board resistance, which puts a limit on what you can actually do, no matter how many ranges you want to put down there, or gain stages or anything else. So at some level, you end up being, theoretically, you're limited by printed circuit board itself. And we're getting pretty close to that up at the tera ohm level. On the low side, the limitation here tends to be that common mode rejection ratio, that CMRR that I mentioned before. So where this actually comes into play, that's why there's a bit more of a range down here. We've got a hard limit to this PCB, but down here you can get a little bit more range, better accuracy. So we've got 99% in the dark blue and 90% in the lighter blue. And so what is happening is basically a high current signal is needed to make these measurements, and with that CMRR limitation, some of that signal can bleed over into the voltage sensing leads, and that ends up giving you a DC limit for impedance measurement on the low side. As you move out to higher frequencies, you start to see that this tapers in, and this tapering is basically an effect of the cell cable. What's happening on the high end is the cell cable itself has a capacitance associated with it. We do compensate for that, but the cell cable itself still has a capacitance that we have to push signal through, get it back out, and so there is a capacitive limitation to how low we can go. In terms of making accurate measurements, this system can do 10 picofarads to 99% accuracy, or 2 picofarads to 90% accuracy. On the low impedance side, you also have a pinching effect, and this is again due to the cell cable, but now it's due to mutual inductance, which we'll come back to in a little bit. But basically, yes, we can compensate for some, but that puts a real limit on what the system can do. So if you're trying to make high frequency measurements out here, you're going to be limited. And if you'll note, this is capped at 1 megahertz, which for this system is the highest frequency limit. A lot of times you'll see systems that have higher and higher frequencies, but if they ignore the cell cable, then you put that on and you watch, this does disappear, and eventually it gives vanishingly small results to the point that you cannot make an accurate measurement at very high frequencies. This is potentiostated. This is why the cell cable is very important, because if you don't have the cell cable, you don't know what these lines are. And different cell cables are going to give you different limits. So on the high impedance, that's our accuracy contour map. That is something that we've done, and we've made good measurements in fairly ideal conditions of resistors. Your conditions may not be the same, and if you're looking to get up at those limits yourselves, you may want to take a look at some of the ways that we can do a quick test on accuracy. An open lead curve is going to show you your high impedance limit for a system. It's theoretically infinite resistance. You have to do this in a Faraday cage. Excuse me. Working and working sense lead are shorted together and put inside of a Faraday cage. The counter and reference lead are also shorted together and put in a different Faraday cage. By having them in separate Faraday cages, you get, well, and actually in our case, the counter and reference can be outside of a Faraday cage. But by having them not in the same Faraday cage, you actually reduce the amount of capacitance that gets picked up between the two. So the way that it should look is like a capacitor. So you get roughly 90 degrees, minus 90 on the phase, and you've got a 45-degree angle straight line going up as you go from high to low frequencies. At very low frequencies, and this one's only going down to a little over 10 millihertz, so not super low, But at very, very low frequencies, you can see this start to roll over. And for some systems, the less, if there's not as good a current sensitivity, you will start to see it roll over at lower and lower values. And that's where that IE range comes over. We don't see it here because we're not going to low enough frequencies, and the system can go all the way up, can make accurate measurements at a teraohm, and we haven't hit 100 teraohms here yet. Excuse me. I should note that this open lead curve is done with a larger than standard signal. This is a 50 millivolt AC wave. Also note that when you're up at this, moving up to 10 to the 14th ohms, even that voltage signal, you're looking at half of a femtoamp for the RMS current value. This is why you need to have a Faraday cage. So that's on the high end. For low impedance measurements, again, energy storage and conversion devices are the most common systems that we see that do have low impedance values. The ESR, equivalent series resistance, causes efficiency loss. Power gets dissipated as heat. And when you're assembling multiple packs together, this can lead to thermal management issues for full battery packs. Low resistance devices, first off, testing them potentiostatically, because tiny AC potential can lead to very large currents. And by the time you shrink that applied potential down to something where the current is manageable by the potentiostat, it becomes very, very, very difficult to control it. It's a lot easier to flip the things around, to apply a current signal and measure those very small voltages than it is to try and control those very small voltage changes. So I always recommend that people use galvanostatic EIS for low impedance devices. And where that transition occurs is sometimes difficult to manage. If your maximum impedance on a system is less than 1 ohm, galvanostatic EIS is probably going to start to be a good idea. But some systems will start out at a relatively low impedance in the milliohm range, but by the time they get down to 1 hertz, that impedance may climb up to 10 ohms. And for that type of system, even though the high frequency component may be slightly better to measure galvanostatically, that current signal that you use there might be too large to do the lower frequency, higher impedance. So the exact transition is kind of tough to gauge. By the time you get to a lithium-ion battery that's an 18650 size or bigger, you're almost definitely going to be using galvanostatic EIS. Those are in the single digit to tens of milliohms. 100 milliohm is the most you're likely to see. We do have a hybrid EIS mode, which is helps for some of those transition systems. It's using a galvanostatic control, but it adjusts the galvanostatic signal at lower frequencies to keep the system linear, to keep from having too large of a current signal for the higher impedance portions. So, mutual inductance. I mentioned that this is a limitation for high frequency, low impedance measurements on that accuracy contour plot. The mutual inductance is coming from the cell cable, and basically it's giving an inductor in series with the electrochemical cell that we have. And this is, voltage magnetism, current voltage, and they move across each other. And the electromagnetic field that you generate by running current through gets picked up, that you generate in the current leads, force leads, gets picked up in the sense leads, and this gives you signal. This is an artifact. You don't want to have it. It can be negative because a lot of these artifacts, the way that they work, this is also true on the DC side where the resistance, the system resistance can actually show a negative resistance. Negative resistance, negative in inductance, these are artifacts of the system. They're not, and that has to do with the corrections and the fact that it's not actually representative of the signal within the cell itself. So when you're measuring low current devices, and this is mentioned in the EIS talk for batteries, it's also going to be mentioned again because it is very important how you connect your cell up. When you are measuring low impedance devices, you pair your force leads together. So you're working in counter electrode leads and your sense leads together, working sense and reference. You use twisted pairs. By twisting them, they cancel out that electromagnetic field cancels out and minimizes the amount of pickup. And you separate the force leads from the sense leads as much as possible. This minimizes the mutual inductance within the cell. So, what is the equivalent of the open lead that we did for the high impedance is going to be a shorted lead for low impedance. So for a shorted lead curve, you're going to basically short all the leads together. And you're going to see two components of this. One is that in mutual inductance. So, and this is done by optimizing the cables. So they're separated as much as possible. We've got them twisted pairs, and they're connected from opposite sides. So this is as good as that can do for this shorted lead curve. And it is tiny, but it is still present. And for a lot of actual samples, we'll see this, the mutual inductance from the cell cable and the system is actually the bulk of the high frequency inductance that you see. For low frequency resistance, note that, so this is inductive, and once we leave the inductive region, we get to a part where this is basically where that CMRR comes back into place. This is the limitation. In this case, it's about 67 nano ohms. When you're running your own shorted lead, you should note this shorted lead is designed, it was set up such that there is zero contact resistance measured. That is, we're making, it's that 4-terminal measurement, but also so that both of the sense leads are tied to a single point. So there is no voltage drop across them due to current flow through a brass body that is being used for this. If you actually take a chunk of metal and make distinct connections for the current to for the sense leads to it and the current leads, you will actually measure. You can measure a resistance through that. We use copper braid for a quick and dirty test, but copper braid gives you a about 10 micro ohms per millimeter, or 20-30 micro ohms per millimeter, and you can get a measurable impedance through a copper braid with a system that is designed to measure low impedances. So there is a lot of specialty into the way we are doing this, and I'll come back to a different type of shorted lead curve in a little bit. Again, this is the inductive region. So that's kind of like the system and where our limits are going to be, high and low. So there are a lot of ways to make bad measurements. Many ways to make them. But some ways of making bad measurements do happen more often than others. First one, for low current, high impedance measurements, use a Faraday cage. This figure is showing that open lead curve from before in red, and a second open lead curve with the exact same instrument setup configuration without the Faraday cage in blue. And you can see two different components. First, we've gotten some more capacitance here because that Faraday cage, the way that it was setting up, was actually helping to block that out. And now we've added a little bit of capacitance back in. Second, and more dramatically, is a huge shift and a big increase in the noise when we get down into the lower frequency, higher impedance measurements. All of these values are just not nearly as good, and there's a lot more noise here. That's all coming from an ambient environment. Faraday cage blocks all of those out. And in short, I mean, impedances over 100 mega ohms, didn't correct that one, should always be made inside of a Faraday cage. On the current side of things, if you're less than a microamp, you should probably be in a Faraday cage. If you're down into single digit nanoamps and lower, you should definitely be in a Faraday cage. And in some environments that are particularly noisy, if there's a lot of pumps going on, you may need to be in a Faraday cage even in the microamp regions. So it is an environmental effect. So where you need to switch over to using a Faraday cage will change from lab to lab. Another issue is grounding. So all of our potentiostats are floating. That means that they are isolated from earth ground. This is a requirement if you have experiments with grounded electrodes, if you're running electrochemistry inside of an autoclave, or if you have multiple electrodes and systems connected into the same cell. This can be like a bipotentiostat experiment where you've got two working electrodes, one reference, one counter. It might also be different actual systems. For a lot of fuel cells, the two terminals of the fuel cell are actually connected to an electronic load that sinks high DC current, and then we use a potentiostat to put a small AC signal on top of that. But because that electronic load is earth grounded, you've got a source of earth ground in the system. And this is true for most other pieces of equipment. So people that have additional voltage leads that they tie in for sensing, or for different types of devices, or if they've got other electrodes in the system that have tie back to an earth ground, you may need to use have a floating performance. Our cell cable has a black lead. That black lead is a float ground, because even though the system is isolated from earth ground, it still has an internal float ground reference. When you're using a Faraday cage, you absolutely have to connect the float ground lead to the Faraday cage. Earth grounding can help reduce noise if you have very low current signals, very high impedance, and you do not require the floating performance of the potentiostat. You can earth ground the system to help reduce the noise. If you want to earth ground a system, it is important to only use one point of ground for earth. There is a ground lug on the back of our systems that is usually the one that we recommend. You plug that in and you tie it to an earth ground source, and then you short the black lead to the Faraday cage, and you leave the Faraday cage floating otherwise. However, if your Faraday cage is already earth grounded, when you connect the float ground lead of the potentiostat to that Faraday cage, you have earth grounded the system, and you need to leave the ground on the back of the system disconnected. If you have multiple contacts to an earth ground, you have created a ground loop, and you actually can increase the noise of the system instead of lowering it. Another source of issues for actual measurements are high impedance reference electrodes. Back on that 3 electrode slide, we took a look at the fact that we were connected a lead to the reference electrode, and I said we don't measure the impedance of the reference electrode. And while that is true, that doesn't mean that the impedance of the reference electrode has no impact on the device performance in the system that you're measuring. So here are 2 EIS spectra that were recorded on a simple 2 kilo ohm resistor. Upper frequency limit was only 100 kilohertz, so we're not going all the way to the top there. The blue spectrum is what we would expect to see. This is what we normally see with a setup For the red spectrum, we just put an extra 10 kiloohms on the reference lead. Now we're not measuring that when we get down to the DC, you see, or when you move to the actual impedance modulus here, you see we're at 2 kiloohms. We are not measuring the 10 kiloohm resistor on the reference electrode. However, what it's doing is it is slowing down the voltage response on that reference electrode. And so as we move to higher and higher frequencies, that really starts to show up first as a deviation on the phase measurement. But when we get to, I mean, we're only at 30 or 40 kilohertz here, and you can see that it's already having an impact on the actual impedance modulus measurement as well. So high resistance, high impedance on the reference electrode, even though that is not directly measured in a 3-electrode cell, it does affect the system that you're looking at, because that voltage measurement has a time constant associated with it. That time constant's affected by that cell resistance. So if we slow down our reference electrode, it starts to lag. If this reference electrode impedance gets too high, then the system can start to oscillate under feedback control. So obviously here, this is only 10 kiloohms, and we're affecting the EIS performance. For a DC measurement like polarization resistance or a CV at a 10, 100 millivolts a second, this wouldn't have any noticeable effect. If this value starts to get closer to 20, 30 kiloohms, all of a sudden even those measurements would start to be problematic. Another problem that comes up is ignoring the capacitance in the connections. This is largely an issue for coatings, where the coating capacitance itself may be at the same order of magnitude as the cable capacitance, but it can happen otherwise. Now, there are a few different ways to deal with this. So this is a high impedance setup. So we've got a 100 kiloohm resistor measurement here. And what you can see is we have paired the sense and force leads. So this is, we've got working and working sense here. We've got counter and reference here. And we have separated the working sense side from the counter reference side as much as possible. And when we actually made the connections to this resistor, the alligator clips you can see are pointed towards each other. And this is the resulting EIS spectrum that we're getting down here. So we're pretty good on both, that we're right at the 100 kiloohms, but our phase is at 0 where it should be, and we start to see a little bit of deflection here as we get to higher frequencies, which you're always going to see. 100 kiloohms you cannot measure to a megahertz with any system. Now, if we make another measurement of that exact same resistor, but now we do our 4-terminal measurement like you would for a high impedance or for a low impedance device. Now we have our force leads over here, so we've got working and counter, and we've got our sense leads over here, so work sense and reference. And what you see is this phase, which even up at 100 kilohertz was less than 2 degrees, is now at 10 degrees. So it's deflected dramatically. And if you line all of these up and bring them in completely in parallel, it gets even worse. So what's happened is these alligator clips are bare metal and are the banana jacks underneath. There is no shielding around them. They are going to have higher capacitance than the shielded cable will before it. Additionally, even with shielding, it's not a perfect block of 100% of the capacitance, so there is additional capacitive pickup even in the cables before this. So we measure through. If you bring all those cables together and they're all aligned, oriented in the same way, you're going to maximize the amount of capacitance that you're picking up across them, and you're going to introduce greater phase errors than you will if you can orient them. First off, pair your force and sense for high impedance only, and separate the leads so that they are farther apart, and so that these alligator clips are pointing at each other. You can't always make an ideal connection to everything. Sometimes you are just going to have to deal with some imperfections in the measurement. But as much as possible, when you're getting up to these really high impedance, this is how you'd like to set it up. You can make port connections for low impedance systems as well. So there are three different ways here to connect a capacitor. This is the worst of the group. So this is using our 4-terminal device as a 2-terminal device. We've got our sense and current lead and force leads shorted together before they make contact with our wire. Also, everything is running in together, kind of parallel. This is as bad as it can get. You can do a little bit better by taking your sense leads and your force leads and doing twisted pairs with them. This helps reduce the inductance, but we're still making a two-terminal connection here. And these are not as far apart as they could be. So the best way to make this measurement is shown here. We've got the sense leads and the force leads with twisted pairs. They are separated as much as possible, and they are making distinct connections to the wire carrying the current here. This is the best setup. And if we take a look at the impedance spectra from these, so it's 2-terminal, no the bad version. If we improve the inductance pickup with the twisted leads, we get a little bit better. But a dramatic improvement occurs when we switch over to that 4 electrodes. So we've gotten rid of all of this contact resistance. This is a 5 farad cap, so it's low, but it's not super low impedance. But you can see that contact resistance, even at a 5 farad cap, is significant contributor to the measurement impedance that we're getting there. Quick note, if you didn't notice, low Z versus high Z connections, the ideal cable setup for a low impedance system is bad for a high impedance system and vice versa. So, and the reason, and in general, what you want to think about when you're doing this is for a high impedance setup, you want to minimize the capacitive pickup that you're getting, and that's coming through the terminals and through the cables having them separated. For low impedance, you want to minimize mutual inductance, and that comes through the force sense separation. And since that's an electromagnetic field effect, the twisted pair does improve that. So these are if you've set up for one and you do the other, you've got a bad setup. Most people, however, are only doing one or the other, which makes things easier. So that's general cable setup for low impedance and high impedance. But when you get down to measuring very low impedance, now that 5 farad cap was 5 milliohms, the cable connections make a difference. What happens when you get down into the micro ohm range? Yes, you still need to minimize the cable inductance. You still want to utilize the 4 probe design. So these are still your setups. But something else that you may need to look at doing is to use a low impedance surrogate or dummy cell. And that is what I'm showing over here. So, there we go. Forgot that. The low impedance dummy cell or surrogate is going to give you the same setup geometry as the actual cell that you want to test. It doesn't have to be exactly the same size and shape, though that might be helpful if there's other types of environmental effects you want to deal with, like setup effects, something that fits in a block. But in this case, we've got a solid chunk of aluminum here that is roughly the same size and shape as this 3000 farad double layer capacitor. We have brass threaded rods on each side for the connections to mimic this. And I should note, it is important to note, these brass threads to that aluminum are going to have a contact resistance, and that is going to be measurable. We can mitigate that, and and I did when this measurement was made, by actually putting our sense lead on the end of the aluminum, and so we're not sensing the current transition from the brass into the aluminum, but we're sensing the end of the aluminum plate or bar on both sides. Whereas the current carrying lead is going into the brass, and because I don't care about the contact resistance for the current carrying leads. The approximate calculated impedance of this aluminum block is about 1.6 microohms. So what does this look like? So I've got the shorted lead on here for reference. This was not quite as good a setup as the other shorted lead. It was a quicker shorted lead test, so we're at about 300 nanoohms instead of 60. But you can see the shorted lead and the shorted lead inductance. Here is that 3 kilofarad double layer capacitor. And what we've got here is our surrogate. So the idea behind the surrogate is to get low impedance, but this low impedance isn't what we're interested in. What the surrogate is showing us is the difference between the shorted lead and the capacitor. There's a lot more inductance here. What the surrogate does is it configures our cables and setup in the exact same way as the actual cell that we were testing. And what you can see in this case is the inductance in the surrogate lines up on top of the inductance that we see in the capacitor by itself. So what that means is that all of this inductance that we're seeing, even though it's a lot more than this a shorted lead, it's due to the configuration. There is the inductance here is almost entirely the setup and not the capacitor itself. This is the same plot. It's just the Nyquist, just because I know most energy device people are more familiar looking at Nyquist. And the reason that we use the Bodhi is because the Nyquist is kind of hard to distinguish down here. Shorted lead spectrum basically looks like a dot. The surrogate spectrum doesn't look like a whole lot more than that. And you really can't see that this is trending on top of this in terms of the actual, because there's a big offset in the lower frequency impedances to get over here. Quick comparison of those results. The high performance system, the system that was used to make that measurement is the best one for making low impedance measurement. When we did a bad test, we got about 250 microohms. When we switched to 4-terminal, that dropped down to about 165. And with 4-terminal and minimized inductance, we got down to about 150. So 150 microohms, roughly, for the ESR of this capacitor with a capacitance of 2,700 farads. The specified ESR is 290 microohms and 3 kilofarads. Quick note on AC versus DC testing. This specified ESR value is probably less accurate than the AC. The specified capacitance, however, is more accurate than the AC. The reason is the AC capacitance measurement is the double layer capacitance only. Supercaps have a tendency to have a lot of pseudocapacitive effects that do not show up in most EIS spectra. You got to go to really, really, really low frequencies, and it's easier to actually get a good value using a DC test. ESR values oftentimes are done at a kilohertz, and if I go back a couple slides here, we can see where 1 kilohertz is on this, and at 1 kilohertz we are, well, this one's optimized. The non-optimized version, it's more obviously up the inductance. So if you don't do this quite right, 1 kilohertz might not be your minimum. So the other thing that you can try and do when you have a surrogate is to do background subtraction. Background subtraction for EIS can improve values, but it has to be used carefully. That surrogate gave us an inductance, and that inductance we can subtract out from our actual cell, actual system, to get at a better version. But what you can see here is one of the pitfalls of doing that. Yes, if you take 16 nanohenries here that you see in the original, and then you subtract out roughly 15.5 nanohenries, this still looks inductive, but if you take a look at the phase, this is going the wrong direction. A couple of effects. One, if you're subtracting anything where you're approaching zero, you're going to get nothing but artifacts. The second one is, if you want to do a background subtraction, you need to make sure that you're subtracting an element that is representative of what you actually have. These inductive, the mutual inductance that we pick up is not a pure idealized inductor. It's actually a constant phase element on the inductive side of things. And so if that's not subtracted out appropriately, again, it induces artifacts. But the fact is, anytime that you're going to go towards zero, it's just not going to work very well for you anyway. It's a lot better for any measurement where you have a known value and another known value. A good example of that is if you have a full cell and a 3-electrode cell, you can measure the full cell, you can measure the 3-electrode cell, and then you can subtract that the 3-electrode measurement from the 4-electrode measurement, or from the 2-electrode measurement, to get the impedance on the second electrode. That works fairly well. It can get you into trouble down here, but if you're really pushing the limits, you may need to. You're just going to have to tolerate a much higher error than you would have otherwise. And so those are kind of the system effects. And now we're going to move a little bit and talk briefly about samples themselves. The biggest one, the biggest issue, because it comes up across the board for electrochemical measurements, is stability. This is an EIS spectrum of aluminum in some electrolyte. People that aren't familiar with aluminum, aluminum forms a nice aluminum oxide film on the surface. A good quality aluminum oxide layer, or basically anodized aluminum, in a neutral electrolyte looks like a capacitor, and you've got a dielectric due to the aluminum oxide, and you've got electrolyte on one side and the aluminum on the other, and so you tend to see very capacitive behavior from it. This does not look good. And why it doesn't look good is because the electrolyte in this case had chloride. And what happens is chloride is a notorious pitting agent for a lot of things, but definitely for aluminum. And because of that, the sample itself isn't stable. So this is the open circuit potential from that same experiment, where you see it started fairly, and then all of a sudden it shifted. And then it spent some time restabilizing, and then it shifted again. And these are pitting events. And it doesn't always look as nice and dramatic as this. Sometimes it just looks ugly. Depends on how quickly pits are initiating, how quickly they're repassivating, things like that. But stability is an issue for a lot of systems. Batteries, especially if you want to do EIS on a primary cell, you can, but the problem is a primary cell doesn't recharge. So you have to do a DC offset in your current so that a primary cell is constantly discharging while you're measuring the impedance. And if your impedance measurement takes too long, you may end up in a very different state of charge and voltage than you started out on. And that does not lead to valid EIS. Any time the background correction can kind of fudge it, but you've got two different systems at the start and the finish, and so you're really not looking at the same thing. Biological systems, and whether that is an actual in vivo, in vitro experiment, or if you're just doing a test out in the real world, rivers, lakes, streams, ocean, where you have biological things that can glom onto an electrode, those change, that biofouling changes the performance, changes the impedance, changes the stability of your system. So if your system at the beginning and at the end of the experiment are not the same, you're measuring, the EIS data is not valid. So how do you fix it? Well, if you can, you change your cell setup electrolyte to something that's more stable. You can also use a smaller area. A smaller area is sometimes helpful because a smaller area electrode is going to be faster responding, and so you can get the low frequency information at higher frequencies than with a larger electrode. But a small electrode area for something like pitting may have a much more dramatic effect when that pit initiates, and so that may not help you at all for everything. But if it can, a smaller area speeds things up. The last thing you can try and do is to speed up the experiment as much as possible. There are a few different ways to do that. When you're running our EIS, there is a little fast, low noise, normal type checkbox that if you set it to fast, it does fewer cycles and runs a little bit faster. You can actually edit the script and change it to force it to do as few cycles as possible, though that's problematic if you get down to low frequencies. Or you can do what I'm about to show you, which is multi-sign. And the last thing is, unfortunately, if your sample is not stable enough, you may just not be able to get the low frequency data out of it, which is unfortunate because low frequency data tends to be more information rich. But if your sample just isn't stable enough to get it, you're going to have to deal with not having that information. There's only so much you can do on the on one side, and you have to deal with the physics and chemistry that happen at the end of at your electrode surface. In terms of speeding up the sample, the way that EIS works, and this is the only part where I'm actually talking about EIS, how it works, is we apply a sine wave, we measure the response, we plot them and fit to get the DC and AC components and the impedance out of this. You repeat this for a range of frequencies, but each frequency is done discretely. What you can and we can do is speed this up a little bit by applying multiple frequencies at the same time. This is just take 3 different frequencies, you add them together, you have the sum of the frequencies, and that signal and its response work just like that. This is 3. 3 isn't a whole lot better than 1 for us, so, well, here's 24. This is 24 frequencies over 2 decades. It starts to look really noisy, but thanks to Fourier transforms, we can take this and we can deconvolute and get the actual independent frequency data back out of it. Our multi-sign does a couple of different steps. So this is a raw randomized signal. Then we deliberately adjust phases to reduce the signal amplitude. So you see here we're up at 15. Now we've knocked that down to 6 or so. And we also do an amplitude optimization where because high frequencies are going to be applied multiple times, and many times more often than low frequency data, we can use smaller amplitudes for the high frequency and lower amplitudes for and larger amplitudes for the low frequency data. So here's our amplitude adjustment, and after we do that, this is the actual signal that gets applied. Still doesn't look like much to us, but thank you, Fourier, we've got we can deconvolute that and get actual impedance out of it. So this is a single sign and a multi-sign overlaid plot. This was a 3 farad double layer capacitor. And you can see that the data is right on top of each other. This isn't perfect, and it doesn't speed it up by orders of magnitude, but the low frequency dominates the time it takes to make EIS measurements. So if you can cram as many frequencies as possible into that lowest frequency that you want to measure, you can get them all out a lot faster than you could if you ran it as a single sign. Factor of 4 roughly difference in the time that it takes to collect the sample, which can be significant. And that's not all of the difficult samples. There are plenty that are just hard to use with conventional cells. And so a lot of times creativity is in order. You want to be able to control the active area and edge effects and things like that, but you can use different setups other than conventional 3-electrode cells. In this example, this is a piece of steel. It's got a curved surface. It doesn't mount very well. It's also got a bunch of edges that we don't want wetted because they have a different behavior than the plane. This is a graphite rod, and we've got a paper towel that's in electrolyte that's making contact. And if we zoom in to that point right there, we can take a look. And so what you see now is the wetted surface is restricted to just the diameter of the graphite rod. So we're not making any measurements from stuff out here. So we know our area. It's the area of the graphite rod. And we can do a 2-electrode measurement with this to get that data. And there's an application note that actually covers this. So with that, I kind of want to leave you with, for when it comes to difficult samples and systems, connections matter. Cable layout matters. Use a Faraday cage if you're on the high impedance side of things, low current side of things. Reference electrode and ground that Faraday cage in the system properly. Reference electrodes can be a source of problems. High impedance on the reference path can affect your EIS even though it's not being measured. And then finally, think about cell setup. If something isn't working, then you may need to change things up. Sometimes there's advice you can find from people that have tried similar stuff. Sometimes you're doing something different and you've got to kind of figure it out yourself. One of my favorite ones was a lab I visited where they were measuring asphalt coatings. And for people that are not familiar, asphalt coatings are incredibly thick and basically insanely high impedance. You cannot measure them. And so the way that the measurement was made in that case was the asphalt coating was put on a piece of pipe that was maybe 30 centimeters in diameter, 40 or 50 centimeters long. The entire center of the pipe was filled and the end caps were plugged so that there was no water penetration to the inner inside of that pipe. And then there was a single wire that was connected on one side to the pipe that ran up out of a fish tank. And there was a counter electrode. And so there was this giant fish tank with this huge pipe, a little reference electrode, and a little counter electrode. You don't need a lot of counter electrode because the current was incredibly small. But by making the area in just very, very, very large, this really difficult to measure sample became measurable. And so, yeah, creativity, trying to figure out how to actually get your samples to be measurable can make a difference. And sometimes you can, and when that's great, great. Otherwise, I'd like to thank you all for your attention and open the floor to questions.
Thank you, Jacob. Yeah, we have a few questions a while. I'll get started with back here just a little bit. Early on, we were talking about the accuracy contour plots. I mean, or just in general, what is considered a good estimate of the change from high impedance to low impedance?
It's not a straight change. I mean, high impedance systems, when we talk about high impedance systems, we're generally talking about things in the mega ohms to giga ohms. When we talk about low impedance systems, we're generally talking about things in milliohms to micro ohms. There's a huge range of impedances in between that. And for most of our systems and most of the time that we're discussing stuff, we don't generally mention it, even though most electrochemistry actually happens in those ranges, because from an instrumentation setup and measurement point of view, they're simple, they're straightforward. If you want to measure something that's 10 kiloohms at 100 millihertz and then tapers down to an RU measurement that's in 1 to 10 ohms at higher frequencies, that's a very normal EIS measurement, and it's not something that you're going to have. Whether you're going to call that high or low impedance really depends on your frame of reference. If you're a corrosion person, 100 ohms is a low impedance. If you're a battery person, they have no idea what you've messed up to get to 100 ohms on the high impedance side. So it's really a frame of reference. In terms of the systems in where when we talk about low and high impedance, we're talking about where things start to get difficult. And so that's tens, hundreds of mega ohms and up on the high side, and it's milliohms and microohms on the low side.
Okay. Another question, can you give some examples of common good sources of earth ground in a lab?
Most modern buildings, the ground wire lead is actually a good source of earth ground. Older buildings, that might not be the case. Older buildings, however, have a tendency to have cast iron and steel plumbing, and the plumbing is usually a good source. Most modern laboratories, anything that's being built with research in mind, actually tend to have dedicated ground points in them. You will sometimes see them. It looks like an electrical outlet box, but instead of having an outlet, it's got a green banana jack, and that's just a ground source for you. And that's general. And so you make do with what you have. And a lot of these research buildings, they actually have a massive copper plate and that is buried in the ground. It's not just a wire that goes to a post in the ground. So they have a really large ground point. But it really depends on where you are. If you've got a good ground or earth ground on your grounded outlets, you can use that. If you don't, plumbing is usually pretty good. But if you've got PVC plumbing, obviously that's not going to work very well. So yeah, that's you might have to do a little bit of hunting if it's not obvious.
Okay. Next, I'm going to unmute Eugene. Eugene has a question. See if I can.
Okay, hello.
Hello.
Hi, yeah. I have a quick question. I'm doing research on corrosion coating protection. And why is it that we don't see the oxide layer sometimes in the Nyquist plot, which is of course represented as an inverted circle or an inductive loop? But when we do some, non-electrochemical experiments such as XRD, we do see those, oxide layers. So do you think that oxide layer is thin enough for the Nyquist plot to detect it?
The short answer, well, you actually do see it, but how you see it really depends.
Okay.
If right, so the aluminum that I showed at the end, all you were seeing was the oxide film there, right? That's why it was purely capacitive. For other materials that are going to form that, you will see it. However, it really depends on how thick it is and whether or not that is the big performance. I mean, Mark Arazam, I think, has several papers that talk about how to study the oxide film layer using EIS, and he's you can, actually has worked out how to get the oxide film thickness data out of an EIS plot, and it has to do with the actual capacitance you see, right? For conventional double layer, electrochemical double layer with a highly conductive electrode with no oxide film that's pushing things further away, you're looking at a distance aspect of something in the 3 to 4 angstrom range. However, oxide films, I mean, aluminum's a really nice one because it's very easy to have it at tens or hundreds of nanometers. For other oxide films, you might be in the, a few to 10, 15 nanometer range. I mean, there's a lot of variation. And so you may not look like you're seeing it, but if you've got a capacitance, that capacitance is associated that double layer capacitance is functionally dependent on the electrode area, the electrode roughness, and the oxide film present on the surface. So all three of those contribute, and they tend to wash together into a single value. And so if you don't have very, very good control over the roughness and the actual electroactive area, getting at the thickness of that oxide film layer gets difficult. And this is so long as it's a barrier oxide, so long as it's a non-conductive isolating. The second that it's conductive or semi-conductive, things change again. So it's not that you're not seeing it, it's just that it's not necessarily disentangled from the other capacitance that you have there.
Okay, thank you.
Okay, do we have more questions? I'm still scrolling through.
Someone raised their hand, I see.
Yes. Okay. So let's unmute Askar.
Thank you so much for your presentation. I want to point out to one of the issues that I face in my research. One of the sources of the issues that I encountered in my research was the loose contact between the working electrode and brush contact or the shaft in my RCE system, rotating cylinder electrode system, and I got very noisy EIS polarization curves, and I could hardly solve that problem. What is your solution for this kind of researches?
So brush contacts, they're almost always graphite brushes. And yes, they are inherently noisy. The fix is to have multiple points of contact to the surface. One point of contact with one graphite brush onto a rotating surface is always noisy. There is no way around it. Having two graphite brushes making contact with that and shorting them together so that your current is going in sensing is through both of them dramatically reduces the amount of noise. More is better, but going from 1 to 2 is a massive improvement in the noise level. But graphite brushes are by themselves a little bit noisy. Mercury brushes are are better in terms of noise, but they don't spin as fast, and you have other issues with people not liking mercury. So almost all of them are graphite, and yes, one point of contact is always going to be noisy. There's no way around it. The fix for it is to have at least 2 points of contact, and that dramatically improves the noise. But it's still a noisier contact point than solid soldered wire connection, obviously.
Yes, thank you. And what is your opinion about using resistors and capacitance between reference electrodes and working electrodes or counter electrodes to reduce this type of noisy curves?
Thank you. I forgot to actually mention that, but here I get to. Yes, so you can, if you have a high impedance reference electrode and there's nothing you can do about it in terms of the Frit's in good shape and the electrode is what it's just high impedance. You can capacitively couple that to a platinum wire or to the counter electrode. And what that does is, the concern with high impedance is that it is slow. And so by capacitively coupling that to a low impedance contact point, platinum wire in the electrolyte, or just the counter electrode if you don't have another good option, now the high frequency component of that measurement response doesn't go through the reference electrode. It comes the other way. It comes across that capacitor, and it comes through the low impedance side and across the capacitor. But having the reference electrode there still anchors the DC central point. And so the low frequency is still referenced to the reference electrode potential, but the high frequency changes now have a path that is low impedance for them to go through. And that does work, and that works fairly well. In terms of setup, I mean, for the capacitor side of things, I think hundreds of nanofarads is usually enough. A microfarad is fine. You don't want it to be too big because then you can get DC drift. So avoid the electrolytics. Just use a medium to large paper or mylar film cap between the two.
Thank you so much for your
Yep.
nice presentation.
Okay, any more questions? Okay, I think we're done. I think we'll stop here then. And we're going to stop the recording and save the chat. So if there's anything that needed follow up directly, we will do that. As a reminder, we'll send the email out tomorrow morning. Our Friday Focus will have a link to this recording if you would like to rewatch it or go back and reference it at some other point in the future. And then we'll have more presentations and webinars coming. We'll send those emails out so you can register and attend the next one. Thank you, everybody, for attending.